Hey everybody, welcome back to Precalculus. Today we're finishing up Chapter 5, Section 1. We're going to be talking a little bit more about angle measures and arc length, area, stuff like that. Okay, so let's just jump right into it. Another way to view an angle is by rotating one of the rays while keeping the other stationary. Okay, so what we can view it as is we have two rays to make an angle, and rotating one of them in a given direction. We'll talk more about that in a second. Okay, and what that'll do is create an angle. And what we call these, the one that stays stationary, we call the initial side of the angle. And the part of the angle that moves, we call this the terminal side. Think about it, that's where the angle finishes. Okay, so angles formed by rotating clockwise are considered negative angles, while angles formed by rotating counterclockwise are considered positive angles. So if we have a little axis here and we think about rotating clockwise first on the positive x-axis, this would be negative 30 degrees. Whereas if we rotated counterclockwise the same amount, this would be positive 30 degrees. Okay, angles that share the same initial and terminal side, so different angles that look like they finish in the same places, are called coterminal. So you put that together with what we just learned about angles moving positive or negative, is think about this. Think if you have a 30-degree angle, positive 30-degree angle. That's if you rotate counterclockwise, it's positive 30 degrees. But if you rotate negative 330 degrees, it will be the same type of angle. It will end in the exact same place, because that's what the word coterminal means. Okay, so we've been asked to find two positive and two negative coterminal angles with 37 degrees. So let's just quickly draw 37. It'll be very similar to the example I just did. Let's just roughly say it's right there. Okay, positive 31 means we're rotating counterclockwise from the positive x-axis. So another way to get to that angle is by doing a full circle, which is 360, and then doing another 30 degrees, which would be 397 degrees. We could even do another 360. So if we add 360 to that, we would get 757 degrees. Okay, so to do the negative ones, I'm going to redraw it here. So let me just redraw this 37-degree angle. Now, one way to end in the same place, to be coterminal with that, is to go negative 323 degrees. Because if we went another 37 after that, it would be negative 360, which is a full circle. Okay, and then we can just do another full circle from there as well, another negative 360, so we should get negative 683 degrees. Okay, let's talk a little bit more angle terminology here. So an angle is considered in standard position. If an angle is in standard position, that's the vertex is at the origin, and the initial side is on the positive x-axis, which is what I've been drawing up above in your notes. Okay, so for example, if we're drawing the angle 45 degrees, it looks like this and rotates counterclockwise 45 degrees. Okay, a central angle is the same as an angle in standard position, but there is now a circle centered at the origin, which is how we're going to make our unit circle. We're going to have essentially a bunch of angles coming off, so on and so forth. Okay, now let's talk a little bit more about a new word for everybody, and that's going to be the radian. So a radian is another way to measure angles. An angle with a degree measure of 1 radian means that the distance covered on the circumference is equal to the same length as the radius. So, if we draw a central angle, which means there's a circle centered at the origin, and I grab my red marker here to show you the length of the radius, okay, the length of that red line. If we take that red line, the exact same length, and lay it around the outside of the circle, along the circumference, the endpoints of that radius along the outside of the circle are going to make an angle here and here. This angle measure is called 1 radian, and we'll talk a little bit more about what that means moving forward. Okay, so given an angle measure in radians, the formula for arc length is S equals r theta, where theta is measured in radians and radians alone. So if it's degrees, you have to convert it. Okay, and given an angle measure in radians, the formula for the area of a sector of a circle, or a pie slice, you could say, is area equal to 1/2 r squared theta, where again theta is measured in radians alone. So if it's not radians, you got to convert it to radians. Okay, let's jump into an example here. So we're being asked, what is the arc length and the area of a sector created by a central angle of 2.5 radians? So our angle measures in radians, that's going to be our theta, and a radius of 5 inches. That'll be our r. Okay, so essentially our equation is S equals r theta for arc length. So it's going to be 5 times 2.5. So our arc length is going to be 12.5 inches. Okay, for finding area, the equation is 1/2 r squared theta. So that's 1/2 times 5 squared times 2.5. And if we do that in our calculator, we should get 31.25 square inches as our answer. Okay, so now let's talk about converting between degrees, which you're familiar with from geometry, and radians, which we just learned about. So let's talk first. A full circle. A full circle is 360 degrees. Okay, and something that you'll learn in a little bit is that a full circle in radians is 2 pi radians, abbreviated RAD. So if we want to see what 1 degree is equal to, we need to divide everything by 360, and we get that 1 degree is equal to 1 pi over 180 radians. So that would mean 2 degrees is 2 pi over 180, and 3 degrees is 3 pi over 180, and 4 degrees is 4 pi over 180, and so on and so forth. And that would be how you convert radians to degrees, okay, or degrees to radians. So the other way around, let's rewrite a full circle is equal to 360 degrees, or 2 pi radians. Those are the same thing. If we want to see what 1 radian is equal to, we can divide by everything by 2 pi. And we get that 1 radian is equal to 180 over pi degrees. So 2 radians would be 2 times this, 3 radians would be 3 times this, and so on and so forth. Okay, now we got some examples. So let's convert 135 degrees to radians. Well, if we know 1 degree is pi over 180, then 135 will be 135 of those. So 135 times pi over 180, which is equal to 135 pi over 180, which we can put in reduced fraction is 3 pi fourths. So 3 pi fourths radians is the same as 135 degrees. Okay, now converting radians to degrees. So 5 pi eighths. So again, we're going to use the same type of formula that we derived up here. We're going to take our 5 pi eighths and multiply times 180 over pi. The pi's are going to cancel out. We're going to be left with 900 over 8, which is about 112.5 degrees. Okay, now let's talk a little bit about angular and linear velocity. Angular meaning how fast is an angle changing, and linear how fast is something moving. Okay, and then we'll do an example at the end. Okay, so the angular velocity. Angular velocity of an object is defined as the amount of rotation per unit of time. Typically, this omega looks kind of like a W, is the symbol used to represent this. The formula for angular velocity is omega equals change in theta divided by change in time. Now, the linear velocity of an object is defined as the change of position or distance traveled per unit of time. So the formula for linear velocity is change in distance over change in time. But on a circle, the change in distance we call arc length. Okay? And if we recall, the equation for arc length is r theta, so we can substitute that in. And if you look here, we have a theta over time, just like we have theta over time right here. So linear velocity is equal to r times omega. So you can use any one of those formulas, but this is how it works on a circle. This is the definition for velocity moving in a straight line. This is the definition for velocity moving around a circle. Okay, so let's take a look at our example here. So if a wheel has a radius of 15 inches, cool, we've been given an R. What is its speed, miles per hour, if it makes 150 rotations, 150 full circles per 5 seconds? Looks like we got ourselves a T there. Okay, so we're being asked for its speed or its velocity. Okay, so we're going to try to evaluate R times omega. So if we have to do it right now, we have to figure out what is omega. Change in theta over change in time. So let's just figure out what is omega. Change in theta over change in time. First, figure out how much the angle is changing every 5 seconds. We know our T is 5. We're doing 150 rotations. And since the angle measure always has to be in radians, we have to know what that is in radians. Okay? We could, to find out in degrees, it would just be 150 times 360. But because it has to be in radians, we know that 360 is the same as 2 pi radians. Okay, so we're doing a 150 full circles in radians. So 150 times 2 pi, which is 300 pi radians. So we're doing 300 pi radians per 5 seconds, which is 60 pi, is our angular velocity. Now our velocity is radius times angular velocity. So we just need to take our radius of 15 times 60 pi, and that should equal 900 pi miles per second. Okay, I'm sorry, not miles per second. This is measured in inches per second. Now last, to convert that to miles per hour, we need to do a little scale change like you guys have done in science class. Okay, first we need to multiply to get the inches to cancel out. So 1 foot per 12 inches, and you see that inches cancels out. We need to multiply by 1 mile per 5,280 feet. So it gets our feet to cancel out. We need to multiply by 60 seconds per 1 minute. So that gets our seconds to cancel out. And lastly, we're going to multiply by 60 minutes per 1 hour. So it gets our minutes to cancel out. And you can see that we're going to end up with something miles per something hour. Okay, so let's do that calculation real quick. And if you do that on your calculator, you'll get that we are moving at 160.65 miles per hour. Awesome job, everybody. Make sure you bring questions to class. I look forward to helping you.